All right, this is now this is the last miracle. This miracle is actually my favorite miracle because it's not something even as esoteric as a radioactive element. It's as simple as a chunk of material. As simple as a chunk of plastic or glass with coatings on it. I mean, it's just that material. You know, decaying atoms are still a little woo-woo, right? Because they get all that random stuff going on in them. But this is just a hunk of stuff. And it's going to work in a similar way. All right. This setup that you see here is a setup that was created by these guys who did this experiment with it. So I give them credit for being clever enough to devise this thing and have it work. And what it is a delayed eraser experiment. And here's how it works. It's really simpler than it looks. This particle comes in, and when it goes through the slit, it runs into a piece of material here that has the property that if it bumps into the right atom, that atom then will shoot off two photons, two particles will take off, and they're entangled. Okay, so that's what happens here. A particle comes in here, it goes through that slit, right there it becomes two particles entangled. One heads this way to the detector, that's the result screen, and one heads down this way. Okay, and in the physics world, this is called the signal, that's called the idler. Two separate particles. Why they call it the idler and the signal, I'm not sure, but that's what they call it. Now, one comes in this slit, two particles entangled, one comes up here, and one goes down here. So they answered the question about does the detector actually affect the particle at the slits? Because here's the detector. These two particles go directly to it. They have no brush with any kind of energy whatsoever in the detection process. All the detection process is done with these idler particles that come down on those two paths. And here's the way it works. If this idler comes down on this path, it's going to end up in really one of two places. Well, there's really one of three, but there's only two differences here. It can get to this. This is just the thing it bounces off of, okay? When it gets here, this is called a beam splitter. A beam splitter is a chunk of material. They used to call them half-silvered mirrors, okay? So there's a 50-50 chance that it'll go through it and a 50-50 chance that it'll be reflected. So it transmits or reflects at a 50-50. It's just a piece of plastic or glass with a coating on it that has holes in it, and half the time it reflects and the other half the time it doesn't. So it's a very simple thing. Now, if it decides to reflect, it goes up into this detector where the time, this just says, oh, I see a pulse at this time, okay? And when it does that, we know if it goes into detector 4, it had to come from slit 2 because slit 2 is the only way to get into detector 4. Okay? The only way to get into detector 3 is if you come through slit 1. So anything that gets in detector 4, detector 3, we know what slit it went through. If it got into detector 4, it came through slit 2. If it went into detector 3, it had to come from slit 1 because there's no other way to get into that detector other than that way. Now, that's the which way data. Now we're going to have the eraser data. What happens if it gets transmitted is it comes here to a mirror, and now after it hits this mirror, it reflects. And it's got two choices. This is another beam splitter. So it can either transmit and go to 1, or it can reflect and go to D2. So it could be either one. It's a 50-50. So this side, if it transmits, it goes to a mirror, and it either comes up here and reflects and goes to D1, or it goes straight through and goes to D2. You see, it's the same thing. You can't tell anymore which is which because the line that comes from slit 1 here If it transmits, it does exactly the same thing as a line that comes from slit 2. It has a 50-50 chance of ending up in 2 or going through to 1. And this way, it has a 50-50 chance of going into 1 or going into 2. So now there's no more which-way information. We've just erased the information. Just like I erased information by having those two paths join before they go into the detector. So that's the delayed eraser. And the reason it's delayed is that these choices of whether it gets measured in a detector for which-way information, here and here, those choices occur long after the signal's already been captured by the detector. So these signals come up, get into the detector. They are either a 2-bar pattern or a diffraction pattern, and they are there before this choice is ever made. So we have a delay, which means after the fact of collecting the data that you're going to look at, we decide whether the which-way data exists or gets erased. Okay, very clever experiment. And it says that no energy whatsoever interferes with what's going to the detector. So we no longer have this problem with the energy of the detector interfering with a particle. That's gone. Anyway, I'm going to use this for my own purposes, the same setup, so I needed to give them credit, and I needed to let you see it when it's simple like this, because we're going to mess it up a little. Okay. There's messy already. Yeah. All right. Now, here's what we're going to do. Notice we have all these little distributions all over it. Here's where we're going to do I think, our best miracle. We're going to have this experiment work the same way, but we have to take it in order. Things happen as delta t's flow around. So the first thing was, first measurement, is we're going to go to the detector. This is the result. This is the final result. And, I should have mentioned, in the original experiment, when they did it, all of the particles, all of these have times on them. Everyone has a time. So this collects time. All the detectors collect time. This collects time, so they can correlate the things that are on the screen with what detector they went into. And they do that with this coincidence counter. All these wires are all the same length. They all get here at the same time. And when this has a detector pulse gets here, one of these is also going to get here at the same time, and that's the one that goes with that detector pulse. So that's how they can match them up. So they know for every spot on that screen, they know exactly which one of these 4 detectors caught the particle. If it got caught in 3 or 4, they got which-way data. If it got the 1 and 2, they don't. Okay, so now we're going to get to this. This is the result screen. So the first thing we're going to do here is we're going to do a binary, and it's going to tell the result screen choice, right? It's either going to be a diffraction pattern or a 2-bar pattern. That's the choice. So we'll make that choice right at this point. That's the first thing to do. That's what we need to know here. That's what's going on the screen. So we put the data on of either one of those. All right. Now, the second thing we're going to do is we're going to come down here to this, also a binary distribution, and we're going to decide what slit did it go through. We need to know that next. So if we decide that it went through slit 2, because each slit has a different path, that's why we have to know that next. We have to know whether we're going to be running down this path or whether we're going to be running down that path. So we decide next we do a binary distribution, and we say slit 1, slit 2. Okay. Now, the third thing we're going to do is that instead of this binary distribution saying, oh, did it reflect or did it transmit? We've already put the result up here. We no longer can let this decide whether it's going to transmit or reflect. Here, we're going to have to decide, did it reflect or did it transmit? And these are going to be single values. Okay, that's going to be these, I have all these distributions up here. Okay, that's the, this is the BD0 here, which decides which slit, right? That's that one. Now we're getting to this one, the single valued, did it transmit or did it receive? So If it decided up here that it was going to be a diffraction pattern, then what is it going to do? It's going to transmit, because it's got to come in here and erase the data. That's how you get diffraction patterns. If we decided up here to get 2 bars, then it's going to have to reflect to go up and get in D4 or D3. And we have to know whether it's going to go to D4 or D3. That's why we had to do this. Which slit did it go through here? Okay. So hopefully you've followed that. I don't know. You know, it's a little complicated, but if you think about it a while, it's not so bad. So that's what's going to happen, and we're going to play that same game on the larger conscious system. Okay, we're going to discuss it in detail, and then we're going to move on to the next one. And you'll see this ubiquitous little microprocessor sitting up here next to where we're going to collect that data on the screen. Now we're going to run this experiment a whole lot of times. We're going to first run sufficient numbers of particles, more is better, through this experimental setup to generate an algorithm. We're going to use that data to generate our algorithm. So that's the first thing. Okay? We're also going to separate our patterns so that the 2 bars fall between the peaks of the diffraction pattern, so we can get as good a separation as possible. All right. So the way it's going to work is after we've run lots and lots of this data, we're going to analyze the data. We're going to make our algorithm here that's going to predict which is which. We've already been through this twice, so I won't have to go through it in much detail. We're going to do that, and then what will happen is that the experiment will run for real now that we've done that. And again, we can do it in the same way. We can do a little 5 nearest neighbors or whatever for the data. So now we're going to run our experiment. And in our experiment, let's say this particle comes in and comes up here, and we pick a diffraction pattern. That's picked up here with this. You'll have to remember that that's what we do here. We pick a diffraction pattern. When we pick that diffraction pattern, then that means when the idler gets here, it's going to have to transmit. So we're going to make this thing transmit if we pick a diffraction pattern. And if we pick a 2-bar pattern here, we're going to make this thing reflect. So this is even a bigger miracle, because now we're not dealing with squirrely atoms quantum mechanically, changing states and sending out photons. We're dealing with a piece of plastic or a piece of glass with coating on it. This is real solid material stuff. And it's either going to reflect or not there. So that's the way this will work. So when we get done with it, we are going to be able to predict from what we have in this recorder here. We're going to have predictions of what's going to happen at this beam splitter. We're going to predict that this beam splitter is going to transmit or it's going to not transmit based on whether we detect here a diffraction pattern or a 2-bar pattern. So it's a similar kind of thing, but it's a little stronger medicine, I think, because it's dealing with chunks of matter, not with atoms, little invisible atoms. This is just a chunk of matter. It's a beam splitter. It's a piece of glass. So we'll predict that. Now, you take this beam splitter out of here and you run tests on it, you'll find it's 50-50. Half will reflect, half will transmit. It's entirely random. Can't be predicted. There is no way. It's absolutely impossible to predict what happens here. But we're going to predict it based on the information we gather when we do our first runs and gather the information and make this microprocessor. So we have, once again, what did I write here? I said, again, I've hopefully managed to put the LCS VRRE between a rock and a hard place, thus forcing it to show us another one of its VR tricks that it's capable of. What we're doing with our microprocessor calculation is bringing each screen data point into the objective common data space immediately, as opposed to not looking at the data until the experiment is over, and then using that computed probability to force the larger consciousness system to manipulate the process of reflection or transmission at the beam splitters to suit its needs. Major miracle. Okay. So, in other words, we're predicting the result of an encounter with a beam splitter before the particle ever gets to that beam splitter. Something that is fundamentally impossible and materialistic in a materialistic universe. That just can't happen. So we shall see. Now, I have a note down here. It says, remember, I said that, but I actually didn't say that, so I'll say it now. If we look at this quantum mechanics, and it's been around for 100 years, this double-slit experiment. These delayed erasers haven't been around that long, but they've been around for 20 years, 30 years, where they've done delayed erasers, at least complex ones. I'm suspecting they probably also did some simpler delayed erasers, sort of like the ones we did, even way back in the 20s. But this information has been around for a very long time, and it stayed weird science for a very long time. It's just not understandable. Feynman words. It'll never be understood in a normal way we think of understanding. In other words, we'll never be able to give it a materialistic explanation. It just refuses to fall to a materialistic explanation, so it's just weird science. Now, given that you've had 100 years worth of very smart people thinking about this problem, having to deal with weird science, and they'd be very famous if they, could solve this problem, because it's embarrassing to have weird science. It means you really don't know what you're talking about when you have weird science. That's the bottom line. So it's obvious to me, and I think to anyone who thinks about it for a minute, that the reason they can't find the answer is because they're not looking in the right place. The reason they can't find the answer is because it falls outside of the box that they're trapped in, which is their materialistic beliefs. They can't find the answer because they're looking at it from the wrong perspective. They're looking at it from the materialist perspective, and it just doesn't work. You see? So that's why they couldn't find it. So it's outside of their set of things that are possible, outside of their set of things that you can even think about rationally. What that means is that if it wasn't bizarre, it couldn't possibly be true. So when you come up with a solution, you know that it's going to be bizarre. It's going to be totally out there, past the point that anybody has been able to think about it yet. Not because it's so complicated, but just because it's outside of the box that they're trapped in. So yes, what I'm showing you, these quote miracles, it's a little bit of humor in that, but these things that are impossible is something that is really far out there. But if it wasn't really bizarre, if it wasn't crazy, it couldn't possibly be true. Because the only solution to this problem is a totally different perspective than what they've been looking at it for 100 years. That perspective isn't getting them anywhere. So the fact that this is so wild and out there, how are you going to make a beam splitter transmit and not transmit, or reflect before, you know what that is, even before it gets there? Impossible. So scientists just don't think that way because it's impossible. There's no point in thinking the impossible. So anyway, the fact that it's really strange, it's really out there, and it sounds a little crazy, that's its best point, because otherwise it couldn't possibly be the truth. So let's see what we've got next. We've got more discussion of experiment 5, and then we come to chaos. Now, Many of you who don't know much about physics probably don't really get this chaos thing, but it is a pretty major discovery 20, 30 years ago that our reality is chaotic at its roots. And that was a big deal because physicists always thought of it as well-behaved. And it is reasonably well-behaved in some regimes. But if you actually push this reality a little hard, it goes chaotic. And that means small changes drive large changes. Little tiny change here makes a real big difference someplace else. That's really what chaos means. It doesn't mean random nonsense. It means that little tiny things here make big differences. Okay, now one of the ways that they looked at chaos initially was fluid flow. They were looking at really at weather patterns. But if you just have fluid flowing in a pipe, if the flow isn't too strong, it just flows. It's called laminar flow. It's nice and smooth, and all the water just travels right down that pipe, just like you'd expect it to. If you make that water go faster by putting more pressure on it, what happens is it doesn't just go so smoothly. You start getting little eddy currents and little things that are different going on, seemingly random all over the place. And that's because the inside of that pipe isn't perfectly smooth. And the water molecules have both adhesion and cohesion, and these are all little things that in a nice low flow, they're small. They're so small they don't make any difference, so you don't see them. But when that flow gets pushed up fast enough, these little problems that it has in its linear flow start to become big problems. And then when a little speck of water kind of gets thrown up because it hit a little bump, that interferes with the other water, which scatters it, which hits other things. And pretty soon you have stuff bouncing off all the walls, and it just goes nuts. And the whole thing turns to chaos inside. And that was interesting enough. But they found out if they just kept on pushing it faster, they'd find little islands of perfect calm with chaos raging all around it. And these little islands would drift and float around among the chaos. And they would change their position, their places. So you have chaos and tranquility coexisting in the same system, coming and going. You know, what was placid becomes chaotic, and what was chaotic just smooths down, and nobody had a clue why. Why would it do that? Why do we have, I can see it's all chaotic or it's all smooth, but why do we have this chaos and tranquility, all one of them turning into the other, off and on, slowly, not erratically, but slowly. And they found mathematics that could predict this and could describe it. It's basically, you need 3 nonlinear differential equations that have iterative paths, and that probably doesn't mean much to many of you, but there is mathematics that describes this and actually shows this chaos and this tranquility intermixing and seeming to cause each other. But the source of this is like, why see a constant and why are probability distributions best describe particles? You know, it escapes people. And the fact that our virtual reality is rendered by this process of taking random draws from probability distributions of the possibilities is the root cause of chaos. Now, this I would call kind of the beginnings of a hypothesis, maybe not even a strong hypothesis, but this is an idea that seems to have merit and is testable. It's another testable idea. So this is kind of conjecture in my part. Okay, so the driving parameter, which is the feedback, which is the water flow, that would be the speed. The driving parameter would be the speed of the water, pushes up the number of possibilities. Because when it goes fast, it can start bumping and changing directions. It's got energy now to do things with the fast motion. So now the possibilities, there are a lot of possibilities. Before, it could just not do much other than travel in a straight line. But the extra speed puts energy into it, and now it can bounce and bump and run into each other and start being chaotic. Okay, so the possibilities grow. Okay, which means the complexity grows. And the more complexity you have, the more possibilities you have, and that grows. You see, so we have positive feedback. You know, the chaos causes the complexity. Complexity causes more chaos, which causes more chaos, and it just keeps going around. More choices, more chaos, and it builds up. But every subsequent calculation has a flatter probability curve. Okay, because before, and let me switch to the next one of these to continue to describe it. Okay, so here it was with this laminar flow, nice and smooth and steady, and this is like maybe velocity down here. Maybe just a component of velocity, or maybe you could, whatever, but it's the velocity, that's the driving factor. So all the velocities were all right between this point and this point. All about the same, very little change. It all flowed together. Everything was moving together, and it was nice and smooth. All right, now you speed it up, and you're starting creating these things. But when you create these, the peak comes down, because now you're putting energy out here under these other curves. So the peak starts to decrease a little bit. You put more in, the peak comes down because you're spreading out through all sorts of things. Now you're getting more and more possibilities, right? When you take that random draw, here's this little chunk of water. What's it going to do next? Oh, geez, now it's got 50 things it could do. Before it had just one, which is flow along with the crowd. Now there's 50 things that might happen to that little chunk of water because stuff is buzzing in all directions all around it. So now you randomly pick one. And of course, some of those random picks are going to be out under the tail because we're talking about lots of little chunks. Every little chunk is its own little unit. So we're talking about, you know, millions of these random draws. So you're going to be having lots of them coming out under tails of the curves, whether they're the middles of the curves. So this chaos drives itself. But then you get to this point where the curve now is getting flatter and flatter, faster and faster, more and more chaos. And here's a place where there's a little less chaos. Then it gets more. And as it gets more, of course, it shrinks down. Well, what happens here is that now you've restricted the choices. You're restricting the choices because all these things are almost likely the same probability. I mean, yeah, they're jumping up and down a little bit in the middle, but suddenly the probability is getting smoother because it's getting so frantic that it's actually reducing the number of choices. Because you have very little energy here and the choices are all very similar. Well, what happens is where this gets really big and where this is dipped and you got a lot of things going on, that starts to end up over here as an area of tranquility. That starts to open up in a more placid state because you really don't have that much change going on because everything's been squished. So that's why we have these areas of very rapid, high, frantic, chaotic motion. They start to turn into this. In these areas where it was a little more expanded and you had different kinds of results, things could be going this way and that way instead of everything just this and that, this and that, this and that, just little bits of amplitude, little bits of differences here in the probability. So these all have about the same probability. Now you're starting to get difference of probability between here and here. So as you do that, you're getting more clear differences in your random draws. So what happens is then you're going to alternate these areas of shrunken amplitude, and this is probability going up here, and this is like velocity here. These shrunken areas of probability are eventually going to turn into this because there's fewer choices. So the same thing that drives the chaos also drives the chaos into placidity. And they're going to alternate. And then once these things get to be broader, you start the whole process over again. Now you're back up here. And now you can start adding little things to it. And this thing will eventually erode, and there'll be other places that tend to calm down. So it looks like this whole idea of chaos is really just driven by this one idea of taking a random draw from the possibilities. And the way to check this would be to use some really strong computer code that would break this fluid up into little tiny pieces. if you like, think of a whole bunch of little specks, little tiny pieces that were buoyant neutral. Means they didn't float or didn't sink. They just stayed wherever you put them, and as far as the fluid goes. So they'd go wherever the fluid pushed them. But you put thousands of them in there. So each one of them was just a little spot that would go wherever the water. And then in your computer, you track where all these spots will go. And the way you do it is you say, well, what are all the ways they could go? What are all the possibilities on this? And you have to look at all the forces on it from all the other specs. And then you say, we'll take a random draw from that. And then that's a random draw. That's the way it goes. And then you have to do that for every spec. And then after you move them, you have to do it for every spec. It's going to be a hugely intensive computation. But they have software that does this sort of analysis. They do it for a lot of complex element analysis that they do would kind of fit into this. So one could do this and keep using this principle to see whether indeed that does then produce results that look like chaos. So those are my thoughts on it, that we may have a solution, a root cause of chaos, just in the way this one part of the virtual probability works, and that you get random draws from probability distribution of the possibilities. And that might be the root cause. What do they call it? Something element analysis. None of your software guys, huh? Finite element analysis, yeah, it's the kind of software that does things similar to this, where they break everything into finite elements and then they track how they move. Yeah. Yeah, yeah. So that would maybe be a way to do this, to test this idea, to see whether that isn't the root cause of chaos or not. Now, I don't have a lot of confidence in that either way. It just seems like it's plausible. It's an idea that came to me, and I would very much like somebody to do the math and the computer science to see if that would substantiate itself. If so, then it would provide a reason for the chaos. So that then is the very last slide I have. All my miracles have been divulged, and now. Thank you. Now, my hope is that some enterprising scientists out there will take these up and actually do them so we can find out, what the answer is. Because either way, science wins. However they come out, whether they come out supporting my view or not, we'll all learn something. That's how our views get changed. That's how theories grow. If you find out you're right, well, that verifies what you're doing. If you find out you're wrong, well, that gives you new directions in which to build in. So it's all good. Science gets a plus up no matter how they come out. The only reason that science doesn't get a plus up is if they don't do the experiments. So I hope that they will, I can convince somebody somewhere to go do these. They're not that expensive and they're not that hard. So folks, if you're listening out there and wherever you come from, and you can do these or know somebody who can, please help me out here. So that's it. I hope you guys don't have headaches, other than I know.
It was just a blur. It's gone.
Good. I'm glad to hear that. I'll make it up to you tomorrow when we won't talk about physics unless you really want to. Okay, we have time for questions. I suspect there's probably a few thousand questions now. So we have about an hour to work those off.
I was curious, what is the cost for something like this?
Well, it depends on who you are and what you have access to. Take a major university. Take a major university like Caltech or MIT or Harvard or University of Pennsylvania, just making up universities. They probably, I give them about an 80% chance that they have most of the equipment necessary for this sitting in a closet someplace in a physics building. This is a standard experiment that's been done for 100 years. It's so dramatic that a lot of people like to do it just to see that it really works. So most places have done this kind of an experiment in the past. Now, if it's 50 years ago, they probably still don't have the equipment. It's probably old. But if it was in the last 10 years or so, they've got equipment they could pull it out and do it. So it's not that hard. If you had to buy everything from scratch, you'd probably need, you know, I don't know, not a lot, $50,000. Not even that, you know, to buy the lasers and the crystals and all the stuff that you would need. Huh? A couple of $1,000 for the equipment.
And then it's all your time.
Yeah.
Well,
And then
why
you'd
don't you do it?
So just a couple of $1,000s. And then you'd need the people who knew how to actually use that equipment. The people who'd done it before. This equipment is very precise and very, you know, very sensitive and has to be calibrated just right. So you'd need some experienced scientists to at least be involved in the program so that they could put it together. And you can do bad experiments as well as good experiments. And good experiments take time. So I would say that for, you know, a few $1,000s and probably a month's worth of time, you could do all of these experiments, every one of them. And that's all the A, B, C, D, E's, and F's, all of them, in probably a month's time. Because once you got it up and running, these things would go one after the other after the other. It doesn't take that long. The longest time would just be the data runs when you want to collect thousands of particles. But even that's not too hard because you can let thousands of particles come through in a second. I mean, the machines are very fast. They can count that stuff. We can't, but they can. So even the long data runs wouldn't be that long. So it's just not that hard or that expensive, which is why I limited myself to this kind of an experiment, because I wanted it to have the highest probability of getting done. So it's not a big barrier at all. They could do it. If they had the interest, they could do this. Now, if they have any little hope at all that what I'm saying is correct, they'd probably want to do it. Because whoever does it probably get their names in the book that would last a long time, because this is going to be major upheaval in physics. Even without the miracles of, you know, making things decay according to your schedule and making beam splitters, you know, transmit or reflect to suit. Even without that, just the envelope experiment, the ones with the thumb drives, that is the equivalent of tossing a grenade under the tent, you know, of physics. It's going to just scatter everything, because everything they thought they believed in now is clearly not true. They had that with the double slit originally, but it's real small. We don't know. Weird stuff's going on there. We just can't see it. And we'll find out. We'll figure it out one day. You see, it's easy to blow that off. These are so direct and simple that there isn't possibly any other way to describe this that I can think of other than the fact that it's just the way I say it is. They're just that simple. There's no complexity in there as far as physics goes. So it's not that hard. It's very doable. It just takes the will to do it. Now, most physicists would listen to me say that they're going to make a radioactive element decay to the half that you know, they want it to, and that these crystals will transmit or reflect on demand, and they'll think that's so absurd that they won't want to bother. But today, virtual reality is a much bigger deal than it was even 5 years ago. Today, it is the thing. So I'm hoping, that's why I waited to bring these out now, because I think now the probability that somebody will take them up is much higher than it was 5 years ago, and much, much higher than it was 10 years ago. So I'm hopeful. I am hopeful that in the near future somebody will do these, and it won't just be somebody. Then somebody else will have to corroborate that and corroborate that. Science is done all over. Different places do the same thing and see if they get the same results. So I would say within, you know, a year, we might have some results here. I'd be thrilled if it was in 6 months. If people were here wanting to do it, it could be within a month or two. But I'd be very happy if it was in a year that these got done. But if they turn out to work the way I say, you won't miss it. You'll hear about it because it'll be news.
First, I want to thank you, Tom. I'm a psychologist by background. My wife's an accountant, and this was very challenging. But about halfway through, we both had an aha moment, and it's much clearer in my mind. Somewhat pertinent is I got my degree actually in China. My mentor is now at the City University of Macau. He's very friendly with the dean. and I'm going to do everything I can to see if I can influence them to actually do it, do these experiments at the physics department. I contacted him before I came here saying, I'm coming to this thing. It's not psychology, but it kind of, well, I mean, it's whatever it is. I don't know how to categorize this.
Weird.
So maybe I can talk with someone in MBT to
Sure.
follow up to see if we can actually get, I mean, it's a very small
Yeah.
city university, but they do have a physics department.
Right. Well, what we plan to do is to put this out on YouTube and to also put it on DVDs. And anybody that's interested, we'll give them a DVD.
There'll be follow-up to
See?
this, I hope.
And this should happen just as soon as Justin, our man back there with the technology, does the editing and gets it published. Right? That's when it'll happen. So we're going to have to give him some time because altogether we're going to have, 12, 14 hours worth of video, which is not trivial to process. That's a lot to do. So when he gets it out, then it'll be on YouTube. And at the same time, I will make these slides available. MBT Events would be the place to go, www.mbtevents.com. I'll make these things available so you can look at my slides. The slides will be cut into the video so that you can read them. You can get the DVD. I may even, if I can, I may even put my notes pages where I have notes on the slides. It's PowerPoint slides, so I have notes on the slides. I can publish those too, so you can people can see what I've got in my notes. So I'm going to put it all out there as quickly as I can,
Yeah.
and it'll be available. And we'll just send DVDs around to whoever wants to take a look.
Great. My question is actually a little different. I'm very frustrated that it seems like mainstream science and physics is characterized by like what's going on at CERN with the Large Hadron Collider. Just spending so much money, and now the governments of Japan, China, and Russia have announced they're going to spend trillions of dollars to make ones that are about double the size. My question is, they keep thinking they're going to have a breakthrough. Well, they found a God particle. That didn't lead anywhere. Now they're finding even smaller particles. So my question is, under the MBT kind of structure, will they ever stop finding smaller particles?
No, not for a long, long time. Here's the way that works, is that in this virtual reality, there's a certain resolution, and that resolution can change. That resolution tells you how small a thing you can deal with. When you hit the bottom of that resolution, you won't get anything smaller. You'll be at the end. Well, the system can always change that. You know, we talked about that. Keep C closely the same, but up the resolution. So you don't even know that they're going to stop there. Resolution can go up. Anyway, that's how it is. But as long as you're not getting close to the bottom of the resolution of the virtual reality, you're not down to a pixel yet, then you can still break it apart. You can still break it apart, and then you can break that apart, and you can break that apart, and so on it goes till you hit the resolution. Well, what's the resolution? In distance, it's about 10 to the minus 44 meters. Now, time, it's about 10 to the minus 44 seconds in time, Planck's time. In distance, it's about 10 to the minus 36, something like that, meters. So if these particles are much bigger than that, then they got a ways to go yet. You see, so that's where that goes. Now, what they've done is they have this thing called the standard model. And the standard model is very much like the periodic chart was to chemistry. Periodic chart in chemistry labeled all the elements according to the number of protons that are in the nucleus and the kind of electrons they had, you know, how. And then they had rows that all meant something and columns that meant something, and they could find holes. They could predict. And they said, oh, look, there ought to be such and such an element here with these properties, because we've never seen it, but there's a spot for it in the chart. And mostly they looked for those and they could find them. But eventually they got to the point that they were only finding them by creating them. And they only existed for microseconds. So they had to do nuclear physics, basically, to create the element. Okay, they could find it there, but it's not like you can go out and dig in the ground and find this element, you I don't know what they are, Einstein and stuff that's way up on that end of the chart. These are things that are unstable. These are things that don't last. These things that aren't found in nature. And you can spend a whole lot of money and you can just keep filling that chart up as long as you have cash to pay for it, right? You just keep building bigger and bigger things and they last for, 10 to the minus 15 seconds and then they disappear. But we found it. Well, you can see how valuable that was to chemistry. Not at all. They got to a certain point and they said, we quit. There's no point. We're not doing anything that's useful. The physicists haven't got to the point yet. They're doing the same thing with their standard model. They've got their standard particle model, and this particle model had a hole in it. And that God particle you referred to, it's kind of a silly name for it, but that particle was one of those holes in a chart. And I'm not sure how many billions of dollars it took to say, yep, we found it. It didn't last long, but we found it. Now let's go in and get the next one, you see. So they're doing the same sort of thing. And eventually, they'll probably get to the point that they'll say, it's not worth it because we're just filling in our chart, but we're pushing it. We're creating these things just to say that they could exist. And that's all. And that's basically the way it is with the physics right now and the particles. So yes, we spend billions and billions of dollars to fill in this chart, but there isn't really any not much value added in it, other than if you're into pure science, that's what you do. You fill in charts. I mean, that's what you live for. So science is going to do it as long as they find somebody who'll pay for it. When they run out of somebody to pay for it, that's where they'll stop. Same with the chemists, right? It got too expensive making these unstable elements that you'd slam them together and then you'd name it something, but it only lasted for picoseconds or something. It's hardly worth the trouble. So that's what's going on there. Yes, it's an awful lot of money, and it'll probably have some good tech spin-offs where they'll find niftier ways of doing levitation or magnets or other kinds of things. So you'll get some back out of it, but it's an exercise in pure science, doing it because it's there for the most part. Yeah, it's just going to get, it'll price itself to the point where it quits. Nobody will pay for it anymore. So if the Japanese and the Russians want to fit a bill to, to get another couple of particles on the chart, there's some status in that, There's some status in being the one that has the biggest atom smasher in science circles. Yeah. I guess there's some infamy with it too, spending all those billions of dollars when other people are barely getting along and able to survive. So there's some infamy goes with that status. And that'll have to work itself out in the future. But I don't think you'll see an end to it until the money runs out. Or until they get to the bottom of, they get to a pixel. Then it'll run out. But I don't know that that'll happen. They're not even close. They're not close to the pixel point yet, so they got a long way to go. So whatever it's worked like that. They used to call these particles like neutrons and protons and electrons, they were all elementary particles. And what elementary meant was they couldn't be divided. They were fundamental and just were the way they were. They weren't created from anything. Well, that's a problem if you're a materialist. They're not created from anything. They don't have a cause. You really have this need to break them apart and see what caused them. And then you have another level of elementary particles that didn't come from anywhere and have no cause. Well, then you have a need to break them apart and see where they come from. If you ever get to the point where, there isn't anything else there, then you have to admit that they don't have a cause. They just are. Nobody wants to admit that. I mean, how many physicists have you heard admit that time and space and charge just are? That's not talked about. People in physics don't, some of them don't even know that. But the very fundamentals of physics just are. Because you can't smash something down later and say, oh, here's a little chunk of space. Here's a little chunk of what they try. And you hear these strange things about space is created by entangled, microtubules that are found in, and you get all this stuff, and it's mostly just nonsense. They're just trying very, very hard to come up with a material underpinning for space and time and that kind of thing. So they work hard at it, but it's really a lot of wild conjecture. There's nothing solid under any of those things. But, science will work as long as there's somebody paying the bills. And enjoy it, too. It's fun work. Other questions? Yes. Who gets there first?
Well, my question is the following. If we're trying to trick the system, and we're successful in that, and we know that the system is much bigger than us and much more intelligent than we are, doesn't that mean that it's actually allowing us to and yielding its secrets without the problem? And why would he do that or not?
Yes, it would be yielding its secrets because, yes, it's probably a lot smarter and a lot better at computer science than we are. Obviously, look at the virtual reality it's created. I mean, that's a whole lot better than what we've created so far. So there are end runs around some of these. Most of those experiments, I could have said, well, they didn't have to do it that way. They could have done it a different way. But the way I picked was the most parsimonious way. And I think that if you know enough to trick it, to basically back it up in a corner to where it has to tell you some of what it goes on behind the screen, that you probably have earned a right to know. It's probably something that is meant for you to know, because that then will put us on a different track. You see, here's the way that logic falls out. Okay, let's say physicists say, yea, verily, this is a virtual reality. Well, the high priests of science have spoken. This is a virtual reality. And as soon as they say that, somebody in the back will go, question, who? Who programmed it? Who's making this virtual reality? Where's the computer? If we're in the virtual reality, then there's something outside of this reality that's creating us. What about that, science? Well, you see, science, if they say it's a virtual reality, are logically also saying this is a subset of another reality that is non-physical, you see, that is creating this. Well, most scientists would rather be staked to the ground, on an anthill, than admit that. That's a really hard thing to admit, but they won't be given a choice. Because once they say this is a virtual reality, there's a whole lot of other people that don't have that much investment in science being pure and materialistic and deterministic. And they'll say, what about, who's the programmer? We're likely to then get into some kind of religious problem. Because every religion is going to say, my God's is the programmer, right? Hopefully that won't last long, because that will not be productive at all. That will be very unproductive, because we know how that goes. Mine, not yours. And that becomes religious wars and all that sort of thing. We don't want to go back there. That would be a very poor place to be. So hopefully, when they realize that what we are fundamentally is awareness, it's consciousness. This is a virtual reality. That means, we've already said, the body is an avatar. Well, if the body's an avatar, then who are we? Well, then we become consciousness. If we're consciousness, then we're non-physical. Has to be. That's the nature of a virtual reality. And if we're non-physical, so is the computer. And the computer is also consciousness, because they're talking to each other. So right away, logic tells us that. And then we lead on to end up with love is the answer, you see. So they won't be able to take it back. Once the genie gets out of the box with this is a virtual reality, all hell's going to break loose after that. And the rest of the world is going to push them or drag them kicking and screaming, into the next step. They can't say, well, it's a virtual reality, but we don't really understand it. We just know it is, and so let's live gracefully with uncertainty there, Yeah, they might do that. Scientists can do that sort of thing, but the rest of the world can't. And things will start to change and move, and probably change pretty quickly. Hopefully there'll be enough people who say, no, it's all a natural system. It's not your God's stronger than my God. My God's a better programmer than your God. You know, it's not going to be this. It's going to be, this is a natural system. And by natural, I mean not supernatural. It's just a system that gets created. It's evolved. And this is what it's doing. It's not perfect. It's not infinite. It's finite. It's imperfect. It's trying to survive. We're a part of that. Survival strategy. We lower our entropy, lowers its entropy, because we're part of it. So all of that is so logical and so straightforward that one hopes that we'll cross all those paradigms rather quickly, rather than get into new religious wars in the 21st century. I think hopefully we've outgrown that. There'll be some that will try, but I don't know that the rest of us will fall for it. So see, that's why it's so important to get the physicists on board. So I think the system is going to give us that because it's pushing us in the right direction. Now we can handle it. 10 years ago, wouldn't have flown. 100 years ago, I had no idea. Digital what? They didn't have anything called digital. They didn't have computers when this stuff was going on. How could they have the concepts of a virtual reality if they didn't even have the concept of digital or computation? So you can't fault Bohr and his friends because they're way beyond them. It was decades and decades before the concepts came around that gives the solution. They did the best they could. But now the concepts are here. Now the concepts are getting popular. They're spreading through the culture. Elon Musk stands up and talks about virtual reality. It's descended down into the mainstream culture, right? So now's the time. And I'm glad of it because we really need that love is the answer. We really desperately need to get to that, and this could be a kick in that direction. And if the larger conscious system thinks that this is the time, then it'll let us see its secrets, because I think once you grow up enough, you're allowed to see the secrets. And hopefully that's where we'll be.
Tom, isn't it, we talked about fractal process, it's almost the evolution of our discovery of knowledge and information, which does come from our connectedness to the larger consciousness system, whether we admit it or not.
Right.
We eventually evolved the idea of digital, digital logic and stuff like that. It's almost the larger system is revealing elements of itself, so we can go back and redescribe itself.
Exactly.
Right? So,
that's the fractal process.
Right.
You see in everything, you see the elements of the origin, if you will, of the way the process works. Yeah, that's the fractal. So it is. Yes. So we finally got to the point where we are big into digital simulation. Right. And then we just got this No Man's Sky, which shows us that on a laptop or a very reasonable computer, you can have a quintillion planets in a universe. It doesn't take, 100 supercomputers netted together. It's just not that hard if you're clever. So then it's very doable. And the time is right. We're getting there. We keep discovering ourselves, if you were, discovering our roots the more that we evolve.
And it also feels that being in the science world, that one frontier to get things moving along is the discussion of where does consciousness lie, right? So the biological world and the neuroscience world is, some of them arguing, you're just the meat pie between the ears, and it's all over when you're over, as opposed to there's something more than that. So there's a whole load of things happening in that arena. Physics will go kicking and screaming, it seems, just from the fact that they've come up with brain theory and the 13 dimensions with hidden dimensions. I mean, those are all ways to just say, it's almost equivalent to shut up and calculate. It's just take the dogma of the Big Bang happened and that was it, right? And then, before that was a brain that collided into another brain. It's going to be a while for physics, but they will get pulled along with.
Yeah, I think they'll get pulled along. I believe the the leaders, I think the physicists will kick it off just by saying this is a virtual reality. They won't intend to make the mess that they're going to make. They think they're just going to say that and that'll be fine, and everybody will go, oh, well, that's interesting. But it isn't going to be that way. When they make that declaration, that's going to set loose a whole load of speculation and ideas, which will generate books by the hundreds and interest, and people be hearing about it. And the whole thing is just going to grow. And pretty soon the physicists will be, the tail trying to wag the dog. They may have started it. They may have started that ball rolling, but they're going to lose control of it very quickly. And they will eventually be drug kicking and screaming into the virtual reality idea and consciousness. But you see what a big turnaround it is for them. I mean, they have to do 180. They've been adamant for 100 years that this is a clockwork universe. Yes, this is a deterministic place. It has to be, otherwise we're wrong. Saying you're wrong is really tough. So, yeah.
Quantum mechanics is the rat hole. I mean, that's the thing where there's the rabbit hole right there.
That's the
And
rabbit hole.
They just put that aside and they just live in the deterministic
world.
world.
Then they're okay with that.
Yeah, right.
See, quantum mechanics, that first double slit experiment, all started when Einstein said, the light's a particle. No, it isn't. It's a wave. Well, let's settle this argument. See if a particle going through double slit can be a wave. Of course, that's ridiculous, and of course it did it anyway. And they've had that thorn in their side for a long time, trying to forget it, but it's the rat hole. It's or the rabbit hole. And that's the same rabbit hole I'm using, because it's simple and it's easy.
It's the thread to go down. Right?
Yeah, right. Pull that thread and it all unravels.
Yes, Tom.
Yes.
Well, I'm curious and I'm ignorant. Could your well, it's true. Could your experiments be simulated in a computer, in a computer simulation, like be rendered in a computer simulation, and could it be cheaper?
No, I think they'd have to be done not in a computer simulation. I think they need to be done, with the real world, because the whole point of them is that you're causing a miracle to happen that can't happen in this world, and any kind of thing can happen in a computer. Computers can end up with all sorts of results. It's just a simulation. Just a simulation. So is this just a simulation? But it's not. It doesn't have the credibility. Yes, it could be simulated to a large degree, but it doesn't carry much credibility that way as the real thing. When you get that real radioactive element decaying according to your predictions, now you've really thrown a wrench, into their works. You've clogged it up really good.
It seems to me that we're about to see another demonstration that science is not a cumulative endeavor, and we may be on the verge of another Kuhnian scientific revolution.
Yeah, I hope so. I think that would be really nifty because we need it. We need it really badly. Yeah, but who was that wrote the book that that said, that told us that science, we think that we keep building on blocks cumulative, but that's not the way it works. We just keep on keeping on because we're not any more imaginative than that other than keeping on. And all the breakthroughs come somewhere else. The breakthroughs come out of the fringe, work their way down into the center and eventually take over. But the breakthroughs hardly ever come out of the center.
And when they occur, all science has to be rewritten.
Yes, it changes everything. And in this case, not only are they going to have to rewrite science, you see, they're going to have to rewrite metaphysics, ontology. They're going to have to rewrite theology. They're going to have to rewrite everything. Psychology, physiology, the studies of brains and the way our minds work, and everything. Everything. Epistemology, everything's going to have to be rewritten. So that's why this is the big one. It's not just that you're going to have to rewrite science and go from Newton to quantum mechanics. This is like, from Ptolemy all the way up, past Einstein, all happening all on the same day. It's going to be a much bigger bang, because it will tear everything up by the roots that we think we believe. And that causes chaos of its own. That causes uncertainty. Uncertainty causes fear. And it's liable to be a rowdy party for a while before it settles out and ends up with love as the answer. So I don't think just one day we'll all wake up and love will be the answer. I think it's going to be a rough ride for a while.
To build on what Alan said, I'm curious where chaos theory takes us, because if I look at that in any system that goes into collapse, well, to use your laminar flow example, you put enough pressure on a pipe, at some point the pipe cracks, right? So is there an analogy there in the chaos model, or how do you apply that? Is there a fundamental transition in this virtual reality that hacks the system to fix it?
Yeah, well, the thing is that, again, it's part of the fractal process. We see this chaos, and we see it in everything. We see it in the way jet engines work. We see it in fluid flows. We see it in the weather. Almost all the natural places we look, chaos is there, lurking in the margins. We just don't notice it because we generally stay out of the chaotic areas. We don't push our systems that hard. But chaos often has to occur before tranquility follows. And what we just said here, it could be that, and it is, that we have to go through this chaos. We have to, there's no way to just drift from being totally ignorant and misinformed to being knowledgeable and at peace. There's going to be a lot of turmoil through this. So chaos is part of the process. So now that's us on a grand scale as a species going through the same processes that fluids do. You see, that's part of this as a fractal system. You see these same things repeating themselves all over. So we will probably have that kind of chaos, and then there'll be little pools of tranquility that'll float around, and eventually we'll outgrow that, and everything will be not back to normal, it'll be totally different, but it'll be relaxed again. Now, does that period take a decade, or does it take a century? I have no idea, but I think it'll take less time than more. If you look at things that were major upheavals, major changes, you can see that the further back you go, the longer those changes had before they worked themselves into the next stage. Industrial evolution. How many hundreds of years did it take us to go from the industrial evolution to the information age? Okay. But I think the information age, well, what are we talking about? The world is information, right? This is the right time. So this information age is going to move a lot faster. So I don't think it's going to be hundreds of years trying to mature with these ideas. I think it's going to be less than that, probably less than a decade. Once that ball starts to roll, my guess is that it's going to roll pretty quickly, which is good. But it is interesting that we see the same chaos, the same things that apply to water in a pipe apply to humanity. And that's because of the fractal process. It's all basically the same sort of thing at the root. And that's kind of reassuring. Because if you look at that, if you look at the idea of systems in cooperation, you can see where we're going. You can see where we're headed. You have single-celled things, just whole lots of them. How do they decrease entropy? They cooperate. Now you have multi-celled things. How do they decrease their entropy and grow? They have specialization. Now you have the locomotion part, the digestion part, the control part. You have all these parts. More complex, lower entropy, more survivable, better machine, right? And now we have us. We're one of those things with the different organs and differentiated. Now it's our turn. We're the new bacteria in this thing, right? Now we have to cooperate. We have to get together. We have to find that caring is much better than fear. And when we do, we will create another organism. We'll be a different kind of thing. No, we won't all be joined at the shoulder like cells are, but we will do it in our way. It's like these cells did it in their way. We're doing it in our way, so we will be a new thing. And that tells you where our evolution's going. We see it, the repetition of it. That's the way it works. So what do we have then after that? Is it us and other worlds, other planets, other places, other solar systems, or other galaxies, or is this just meant for us? And now we get into a mental space, and now we start going out into the larger consciousness system. Who knows? It's kind of hard to think about because it's kind of far away from where we are now. But we are reaching that point where it is now possible for us to be cooperative. It's hard to be cooperative when we're all fragmented and nobody can communicate. Well, the internet and communications technology has solved that problem. If we're going to grow up to be one family, well, we need to be able to talk to each other. The infrastructure for that is built. See, it couldn't happen before now. Now is the time. So I think that's very heartening that we can see the progress and see where we are headed. And we'll get there sooner or later. Rather it be sooner, but we will get there, even if it's later, because that's on our evolutionary path. That's where the path leads to lower and lower entropy configurations of everything. It's our turn now.
I have a question concerning the double slit experiment with the envelopes.
Mm-hmm.
I just want to see what you predict and what will happen if we were to do this experiment. So you do the double slit experiment with the 100 envelopes.
Mm-hmm.
So they come in pairs. You have the pattern in one envelope, the measurement in another envelope.
And both those envelopes in the experiment envelope.
Yeah,
Okay.
yeah, they're in different envelopes. And for each pair, you flip a coin. So head, you destroy the measurement envelope. Right. Tail, you keep the measurement envelope. If my understanding is correct, is that your prediction is that in the pairs where you have kept the measurement envelope, you just see two slits.
Yeah.
And for the envelopes where in the pairs where you have destroyed the measurement envelope, you should see a diffraction.
Yes.
Okay, so here are my questions. Assume that you do this experiment, but you change the order a little bit. You open the 100 envelopes first. You toss the coin next. Then you destroy the envelopes that for which the coin landed on the head.
Which envelope are you opening first?
All of them. You
all
open,
of them?
You open all of them first.
All the envelopes?
You open all of the, no, you just open the pattern envelopes first. Then you flip the coin.
Mm-hmm.
And head, you destroy the corresponding measurement envelope.
Mm-hmm. Yeah, none of that will make any difference. Once you've looked at all the pattern envelopes, you've collapsed all the possibilities. Now there are no more possibilities. So it doesn't matter what you do after that, nothing will change. As soon as you've looked at all the measurement envelopes, then game's over because there's no more change possible.
So what do you expect to see? What
I would expect to see once all the measurement envelopes are open?
No. The pattern envelopes.
I mean all the patterns, yeah, I'm sorry.
Envelopes.
All the patterns are done. Well, what you're going to see when you look at all the patterns, let's see. All right, now you got me thinking about it now. You're just going to look at the pattern. Okay, you will. There's no reason for you to see anything different. You're going to probably see the 2 bars on the pattern. 2 bars, 2 bars, 2 bars. All of them are going to be 2 bars if you just look at all the patterns. Okay? That would be what you see. I don't know why there'd be a reason for you to see anything different than that, because all of the data is still there. All the data is available. You could open that other one and look at it. The data is available. So once you look at it, you have to see something, right? The system has to send you data. You make the measurement, it's got to send you data. At that point, the data it would send you would be 2 bars. So you'd have 100 envelopes, all have 2 bars in them. And after that, there is no other possibility other than have another 100 envelopes that all have which way data in them. That would be the only other possibility.
So the outcome will depend on the order in which you flip the coin and you destroy the envelope. So if you flip the coin,
no, it wouldn't make any difference. Once you looked at all those patterns, Doesn't make any difference what you do, whether you flip a coin or whether you don't or whatever. After that, it's done. You can take all those envelopes and destroy all of them or look at all of them or do anything and nothing changes.
What I meant is that here you have two experiments. In the first experiment, you flip the coins first. You didn't look at none of the envelopes. You destroyed half of them. Then you had some that were diffractions.
Oh, I see. We're going to do that first. Okay, I was out of order. I thought you were going to look at the patterns first.
In the second one, you looked at the pattern first. Then you flipped the coins.
Yeah.
And you observed only two slit patterns.
Yeah.
So that's your prediction.
Yeah.
Okay, that's just what I wanted to.
Yeah, that would be my prediction.
Okay.
So that does make a difference, the order in which you do things.
That's interesting. Thanks.
Absolutely. Okay. Who has the mic? Anyone?
Any more questions, man?
Everybody's beat. When you listen to me talk about double slit for a long time, it just tires you out.
So I have a question concerning the what you would call probably the programmer or the system engineer. So in other talks, you talk about something or someone you call big cheese.
Yeah.
What's that?
Well, when you have a system, a very complex system, you have to have ways of keeping track of your system, what it's doing, how it's working. You have to have some way to enforce the rules because your system has rules. That's what makes the system, and that's what lowers its entropy. So you also have to have some management structure goes along with the system. Now, in the larger conscious system, it's a very, very flat management structure, and it's very, very light-handed, but you have it. And the big cheese is my humorous name for the position of management of what I called in my books end division, of which this virtual reality is one of the games going on. Okay? And games of a particular kind of group up together, and then they have this manager that sees that the rules are being, not being violated, and if they are, does something about them, or it may choose not to. Sometimes people break the rules and get away with it. Sometimes the system's asleep and not really paying attention, and they get away with it. Just like real life, you have to police a system to a certain amount of extent. Otherwise, if you don't, then entropy starts creeping in. If there's no order imposed, then order starts to disintegrate. So the big cheese, I named it the big cheese just because I don't want people to take all that too seriously. I didn't want them to turn it into God or anything else. It's just a management function in a larger consciousness system. And, like there are rules that say that other entities, other consciousnesses that are not involved in this particular virtual reality need to leave us alone. They can't just run rampant in here and pop in and pop out and create havoc and do those kinds of things. So there's a rule. This virtual reality is here as a trainer, and the kids are in school. When the kids are in school, the older kids aren't allowed to run around the halls. It's very distracting. So there are rules, and the rules have to be enforced at least some of the time. So that's what the big cheese is. It's just, see, my model is mostly all metaphor. The larger consciousness system is a metaphor. It's that thing behind the curtain that results in our consciousness. Okay? It's a consciousness system, and I make it a digital system. That's me providing structure to it. It's not necessarily a binary system. Who knows? There may be all sorts of computing that's very different than what I can imagine. I just say that as kind of a metaphor. So then we talk about the big cheese. Well, that's just a metaphor for that management organization that has to be there to keep it from de-evolving with more chaos, without anybody trying to make the rules stick. The higher self, the individuated unit of consciousness, all this stuff, they're just metaphors for functions that consciousness has to perform. So if you have a conscious system and it's going to run a virtual reality, There's certain functions that have to be formed, and the big cheese is just one of them, and big cheese is a silly name so that people don't get religious over this management function. I want to see it as a natural system that just has evolved. I don't want to see it as a supernatural system that is somehow outside of evolving. So that's why the big cheese is just a metaphor for that management. That has to happen. Yeah.
A natural system, like if you touch that, it's going to burn you if it's hot.
Yeah, that's a natural system.
Yeah,
right?
but you say the big cheese, is it more of that sort of like a impersonal?
Oh, no, it's not impersonal at all. Well, I guess you say it is and it isn't. It's impersonal in the sense that it leaves us alone because we have free will to make choices, and if it kept coming into this reality and forcing our choices, we wouldn't have free will anymore. If it said, oh no, that isn't nice, you can't do that. You can have free will as long as what your free will wants is what I want. Well, that's not free will. With free will, you do whatever you damn well please, good, bad, or indifferent, and live with it. You know, you got to stew in your own broth. You live with the reality you create. So in that way, it's a hands-off. Just let the people do what the people do. They'll create a reality that represents them, which will give them the opportunity, the most optimized opportunity to see who and what they are and then grow up. So it's a school. So in that way, stuff happens, you have to deal with it. And there's random things that happen. So everything isn't planned and everything isn't part of a program. There's got a lot of random elements in it too. Some things are planned and some things are part of a program. So now, but the one other thing is, as far as that was the idea of it being a machine kind of thing, right? It just does its job and leaves you alone. On the other half, our evolution is its evolution. It evolves because we evolve. It wants to evolve. It doesn't want to de-evolve. That's its own demise. It wants to help us evolve. So it's very much involved in creating a reality that gives us maximum opportunity to evolve. And if a little nudge here and there to us is going to help us move in the right direction, give us information we can use, you've got it. So now it's butting in, right? But it has to butt in a very non-intrusive way. It can't make a choice for you, but it can give your intuition to help guide your choice. But you still have to make the choice. So it doesn't run over your free will. Your free will is sacred. You can do whatever you want with it, but it can help you make better decisions and give you information. And a lot of times when people have experiences with paranormal things, something happened to them, when they were growing up or yesterday or something that just totally blew them away and showed them that reality is very different than what we think it is. A lot of that happens just to wake a person up. It's not really about the event. It's not about the information they get. It's just a little cold water in the face saying, look, reality's bigger than you think. And that is often given to people who can use it, who take it and say, wow. And after that, they say, I need to find out more about this. And they start researching, they start to get into it, they start to learn to meditate. You see, it's a beginning. So the system will do that, but it doesn't ever make a choice for you or force you to do anything that you don't choose to do. So it's,
well, even here, okay. Even in this world, there's these gentle, loving reminders, helpful forces, and then there's some real, you do this, and that's it for you. You know what I mean?
sure.
So I guess what I'm wondering is, we tend to, what is the word, anthropomorphize things.
Yes.
And so what I'm asking you is, when you say big cheese, we would tend to think of it as some guy walking around,
Right.
as opposed to, it's the universe giving us sometimes gentle, loving coercion or, nudging versus, and sometimes at a certain point,
Kick in the pants sometimes.
Yes,
Sure.
exactly.
Sure. Well, when I talk about the big cheese, no, I don't think of some guy who comes to the office and checks up what everybody's doing. It's just a metaphor. It's a metaphor for a function. And the system in general, everything's part of the larger conscious system. You and me, your dog, your cat, and the big cheese, we're all part of this function, or this system. And the system wants us to succeed. Our success is its success. So it's helpful as it can be without actually making any choices for us. That's generally the way that it works. And sometimes the best thing that can be is give you a hit right between the eyes with something that hurts, because you need to be woke up. You need to get your attention. And that's what you need, that's what you'll get. And if what you get is what you need is a little kindness, a little helping hand, if that's what it takes to help you grow up, that's what you'll get. And partly what you get has to do with just randomness. You know, you just run into somebody, they have free will, and they decide to slap you. Well, deal with it. You know, it's just part of that random stuff out there that you have to deal with, which is also good. So there's lots of components to it. But yeah, the system can slap you as well as lift you up. And it'll do either one of them if it thinks it's going to help you grow up. It does what it thinks best for you. And when you ask it questions, it sometimes won't tell you the truth. If the truth isn't going to help you grow up, it's going to help you blow up your ego, then it's not going to tell you that. It'll tell you something that'll help you see a better way of being. So the system isn't this pure, perfect system that always tells the truth and always does nice things for everybody. It's not like that. It's just a system that wants us all to succeed. Sometimes to help the child succeed, they need a spanking. You know, they need some harsh words, or they need some stand in a corner, or whatever it is you do with that child. So they need that sometimes. Helps them grow up. Same with us.
Oh, okay. Tom, what's the style? The
Parsimonious.
Don't you think it would be more parsimonious to not anthropomorphize this from the beginning and not have a big cheese, because it's going to lead to issues and people grabbing onto that like a god?
Yeah, possibly, but here's the trade. If you stay very abstract, then you don't run that risk. But if you stay very abstract, you're going to lose most of your audience. They won't get it. If you keep it up in this...
Well, you have the larger consciousness system. That's what it is.
Yeah,
it's the rule set is what keeps things...
yeah, but when you keep it abstract like that, people they'll deal with it a little bit intellectually, and it won't stick, it won't mean anything to them. You have to give people metaphors that they can relate to. And yes, there is some risk in that. And I thought about that. You know, there's risk in a lot of things I do. There's an upside and a downside to it. You know, you can't guarantee that everybody will grow up from what you tell them. Sometimes it'll make people upset or angry, and they grow down instead of up because of that. So you never know for sure. But I tried to walk that fine line, and I used the big cheese because I thought people would take it with humor, that they wouldn't get wrapped up around the idea that when I call it a big cheese, you have to know that it's a metaphor and I'm just having some fun. But the function is good. That's why I didn't give it I didn't call it Job or, Yahweh or, something like that would get people worked up. So big cheese seemed like it defused that situation as much as I could. Okay, you took the microphones away. Does that mean we're done?